Some of you are just coming on board with the SimpleX Super, and you really should go back to the original videos because here in part 6 we're going to be getting into kind of the middle of the receiver, which is the BFO and detector section. Let me give you some of the answers before we even begin the video. This section was the most difficult for me so far. I found that the audio part of the receiver was very forgiving. Almost any tube I stuck in that socket that was wired like a 6CG7 worked. You know, all kinds of different tubes will work in that slot. Now, someone said, oh, why don't you use a triode pentode and go for some more gain? Now, if you want to drive a speaker, that's a valid point. There are better tubes that you could use that would give you more audio gain. But for headphone use, the dual triode's just fine. Once we get into the detector and the BFO, however, and we start to use the 6U8 tube and its modern equivalent, the 6GH8, and there's probably others that are in the similar class, you start to see some variations that maybe you're not used to. By variations, I mean, if you plug in 5 different tubes into the same circuit, should the circuit act the same way? Should the regeneration control work the same way? Should there be the same amount of hum or background noise? Should there be any drift in the BFO? Those are the types of variations that I saw as I changed from 6U8 to 6U8A to 6GH8 to 6GH8A. Different manufacturers, different eras, and of course, most importantly, how abused was the tube? Remember, these things were all over the handbook, and they were all over ham magazines during the 50s and 60s, but they really were in TVs at that time. And many of these tubes that I have, and many that you have, are pullouts from those TVs. They're pulls, and they're in various conditions of full specifications or not. So the other comment was in AM, the receiver doesn't work that well. Well, guess what? With the filter, you're not going to get very good AM reception. But I am noticing that comment that someone had about the AM reception being controlled by the regen control. Okay, so AM definitely benefits from the regeneration control. Another great idea to have it on the front of the panel. This particular tube I have goes into regeneration pretty abruptly. Other tubes I put in there go into regeneration smoothly. Others don't have as much gain. So that's the way that goes. So anyway, this is the part 6 of the SimpleX Super. We're going to get into the BFO, and we're going to get into the detector stage, a regenerative detector. Next, we're going to be wiring the detector section. And with the detector, we have 2 coils to be concerned with. We have the BFO coil, which is one part of the detector tube, and we have the detector's grid coil, which is the regenerative coal pits style regenerative part of the detector. So I think we should probably work on the BFO first so we've got something to actually measure. So that's going to concern pin 1, 9, and 8. And this is a coal pits BFO circuit. So let's start wiring. Looks like we need to get a hold of some capacitors and a 100K resistor to get started. Okay, here's an important one, and I've just noticed this as I'm wiring. We know that the coil for the BFO is located up here, and the coil for the detector is here. With the tube the way that it's installed, the tube socket, over here is the BFO, which is pin 9. That's got to go all the way over to here to the BFO, and the detector has to go all the way over here to that part of the tube. So we're going to be crossing the tube twice. That tells me that that tube socket is installed upside down. So we need to rotate this tube socket by 180 degrees. And that means I'm going to have to unsolder everything on it and spin it. But these are the mistakes that it talks about in the article. You don't want to be crossing your sections across the tube. You want to keep your leads as short as possible. And that means we need to spin that tube socket 180 degrees so that we don't get cross coupling, and it makes the lead shorter and a more natural build. So stand by, we need to rotate. Okay, there's something else we need to do. After letting the radio warm up, you need to feel some of the parts. Now, you don't want to get burned, but you got to put your hands on the radio. For instance, the transformer. Is the transformer overheating? This thing's been on for now about an hour. You know, does the transformer feel warm? The output tube's going to be hot. It's running Class A. Of course it's going to be hot. In other words, if things are not smelling, getting hot, overheating, you know you've got a stable receiver. Looking down at the BFO circuit, we can see the grid resistor to ground, the grid capacitor, the 220 going over to the tuned circuit, a 330 picofarad and a 680 picofarad going to ground. Okay, I love the smoke test. I've jumpered the 120K resistor to the B+. Let's see if this oscillator is going to come up. Let's turn the power on. Okay, it went off screen. Now it's going the other way. Ooh, look at that. Oh yeah. I have the probe right on the plate of the tube, pin 1. Beautiful sine wave. Let's see what frequency we're on. Let's go up to the counter. Hello, counter. Here we are. 2256. We're high in frequency. We need to come down 200 kilohertz. So that means we need to tune the coil. Okay, let's apply power again. Let this thing warm up. Okay, 2250. I have the BFO centered, by the way. Let's start turning. So it looks like on the low end I can do 1996. That's 3 kilohertz below 2 megahertz. And it looks like I can go 3 or 4 kilohertz above 2 megahertz. That should be enough for the BFO. So you'll notice that frequency is drifting upwards. So there's something going on with drift with the receiver, the BFO. So we need to track this down and see why the BFO is drifting up so radically. Is it a voltage problem? Or are one of the capacitors drifting? But it could be voltage, or it could be something with one of the capacitors. We need to figure this out. So I have a little setup here that allows me to study the BFO. I was not happy with the BFO's frequency stability. It seemed to always be climbing, climbing, climbing. I wanted to investigate, is it something to do with the voltage? I discovered there was only about 57 volts on the plate of the BFO. And I traced that to the 120K resistor having gone up to almost 180K. You know, without investigating what the tube does at lower voltage, I can't make any assumptions. So I've got a kind of a homebrew setup here where I've got a switch where I can turn the BFO on and off, and I've got a potentiometer in concert with a series 5.7K resistor. I can simulate changing that resistor's value from 5K all the way up to 500K. And I have set the voltage for around 78 volts, which I think is probably where we get with the 120K in the correct situation. What I find is when you're playing with the voltage and you're going from 78 to say 150 volts, let's look at the frequency. As I start to change that voltage, and I'm going to start increasing it, can you see the frequency is going up? I'm at 130 volts now, 180 volts, 210 volts. That's called pushing. We're pushing the frequency by increasing the voltage. Now I'm going to decrease it back down to 70 some odd, and the frequency will go down. So there is some pushing with this oscillator, but it's not bad. The culprit is not the voltage or the voltage regulation. The culprit turned out to be one of the capacitors. And the only way to find that is to actually start substituting capacitors. And in this case, the bad capacitor turned out to be the 680 picofarad capacitor, this guy right here. As soon as I replaced him with another 680, and I think I got a silver mica in there right now, immediately this started to settle down. I'm a little bit happier with the drift that's occurring. So as you can see, it's a lot more happy with the silver mica in the 680 picofarad position. So changing the capacitor was the trick. I put the original 120K resistor back in. It seems very happy around the 70 volt region on the BFO. So let's pull on the hum string a little bit. If I turn the volume full blast up, you start to hear some hum. Of course, we can also hear this generator, so let's bring that down. We can hear the hum clearly now. Now you'll notice that in the original schematic they just used shielded cable to wire the filaments, even though it's AC. Works very well. Instead, I use twisted pairs to connect the filaments. There's no reference to ground. Now, that's probably not a good idea. We do need to reference the ground somehow. One way would be to just simply short one side of the filament to ground. That works. That's why that coax idea is so effective. But I thought I would do something different just to show you the technique. I'm going to put a potentiometer, a 500 ohm potentiometer, across the filament leads. I'll probably use the center tube, the detector tube. And I'm going to have the center going to ground, and we're going to try to null out the hum using the potentiometer. This is a great trick when you're building hi-fi audio amplifiers, by the way. Okay, I hope you can hear some hum. The hum pot is right here, and I'm going to attempt to reduce the hum by turning that pot and trying to null it out. I hope you could hear that I did reduce the hum. Now, I couldn't hear it very closely. Hopefully the microphone picked it up, that it was nulling it out. Kind of a tough thing to do when you have a pretty low hum to start with, but the hum pot should have brought some of that down. The BFO seems quite stable. Not that happy with the control. So that capacitor is not great. And that's going to affect the BFO, of course. But changing regen, changing volume does not affect the BFO. You don't want interaction between the controls. So that's working fine. This capacitor, I'm going to have to look at it and see if it needs to be replaced or if I can try to stabilize it. But a little bit irritating on that capacitor. Not happy with that. But that's the way it goes when you're using surplus and junk components. Occasionally you're going to be limited by that component. So one more thing of note. The regen control does work, but notice this little scratchiness? Again, that has to do with the quality of the control, and also I'm not noticing that it's going into regeneration. It's definitely increasing gain, but it's not going into regeneration. So we've got some things to investigate on the regenerative coal pit circuit. Next, I'm going to try to do a rough sensitivity test. I know this is mismatched. It's just after the filter into the first tuned circuit, and I'm just dribbling some signal in, but I'd like to know roughly what the sensitivity of the detector itself is. So I would like to try to determine the sensitivity of the detector. I think I will start at minus 10 dBm. That's 70.7 on the meter. So that represents 0.1 milliwatts or minus 10 dBm. I will come out of the generator into a pad so I know I have an accurate attenuation factor. And I'm going to install right at the output of the crystal. Okay, so the whole front end is not there. So just imagine the 5 picofarad capacitor coming off the 50 ohm right into the tuned circuit. So it's a lightly coupled input onto the tuned circuit. Now that's a horrible mismatch. I know this is not fair. I should be using a step-up transformer to, get the impedances somewhat in line, but this will be a crude sensitivity measurement. After I've done that measurement, I'm going to do a comparison measurement with a real receiver. In other words, I'll put that same signal into a calibrated receiver and see how that agrees with the number I come up with. So one is a direct method and the other will be an indirect method. But of course I am depending on the accuracy of the meter and the oscilloscope as backup. But I don't really trust my generator being calibrated after all these years. I'd rather use the attenuator as the method of determining sensitivity. The attenuator, I would imagine, is more accurate. And human ear, of course. Can you hear the signal? Can you not hear the signal? So again, this is with the regeneration control fully maximum. And I know I haven't got that set up quite right, but I do have it maxed out. So I'm not in regen actually, so I'm going to have to go back. But let's just see what the raw sensitivity is. This is the minus 10 right in. So let's put in minus 10. Let's put in 10 dB. So that's minus 20. Let's put in 20. So that's minus 30. There's minus 40. Okay, that's 30, 40, 50. That's minus 60. Minus 70 dBm. You'd still be able to hear that with headphones, but that's about it. So I would say we're somewhere in the minus 70s. I can put 10 more in. Just hold that up to my ear. I can just barely hear it. So minus 70, minus 80, I would say is the minimum discernible signal of the detector. Just the detector. And I have not got the regeneration control working yet. I imagine we're going to pick some up. The transformer's rough tuned. I didn't go crazy on that. Let me try to max that out a little bit. Yeah, it's about maxed out. Okay, so that was a good test. Tells you the detector is pretty sensitive even though we don't have the full regeneration working. Now, you certainly want the front end to bring you up as much as possible. It'd be nice to get at least 20-25 dB of gain out of the mixer front end, but I don't think we're going to be able to. Well, by the way, let's put this signal into a real receiver and see how the real receiver can do. Oh, I love that. I just hooked it up to the receiver, and it's measuring -80 right on the nose. Oh yeah. So there you go. -80 is the sensitivity of the detector, and we verified it two ways. We verified it using the attenuator, and we verified it with a calibrated receiver. Just to verify, we're at -10, there's 30, there's another 30, and there's 10. So that's -80. So let's work on the regenerative part of the circuit. We know that the regen control is not getting us into oscillation. Now there's two capacitors that set the oscillation in the Colpitts regen, and that's the 2000 picofarad capacitor and the 47 picofarad. Now the ratio of those capacitors is called the feedback ratio. You know, obviously this is a very low percentage feedback ratio. We have a 47 picofarad capacitor against a 2000. That's going to be a very low percentage number of feedback. That's probably the reason this thing's not oscillating. Perhaps the tube doesn't have enough gain. Maybe this 47K resistor has gone up in value and it's starved for voltage. Or it could be my layout. I have that long wire going, you know, back to the 47K and up to the screen grid. Who knows? But there's just not enough feedback. So the way that we increase the ratio, in this case we want to get more percentage feedback, is either by increasing the value of the 47 or decreasing the value of the 2000. So I'm going to decrease the value of the 2000 by putting a capacitor in series with it just temporarily. And the capacitor I've chosen brings it down to around 1300 picofarads. So that should increase the feedback. Now I'm looking at the scope to see if I'm going to get an oscillation as I increase the feedback. By the way, why did they use Colpitts and not Hartley? Remember, the Colpitts oscillator is more stable than the Hartley because you don't have these mutual coupling effects that you get with the Hartley. In other words, the feedback is determined by the coil and the tap on the coil, but you also have effects inside the coil which can cause instability. You don't have that with the Colpitts because it's done with more perfect components, capacitors. So let's increase the regen control. As you can see, as I fool with the control, I'm on the 47K resistor. I'm right at this point right here. So let's see what happens as I increase regen. Okay, looks like something's happening. We're getting more noise. Can you see that? More noise. Up, there it goes. Okay, we just went into oscillation. Now I would expect, because we have that lower value capacitor, that the combined capacitance is going to be lower, so the frequency should be higher. Let's see where we're oscillating. I'll go up here to the counter. And yes, it is higher, 2009. So we will have to readjust the coil to come back to 2000. But the good news is now we have feedback. The stage, the regenerative detector, is now going into regeneration. And it's at a pretty good level on the pot. It's about the 70 to 75% level that we go into oscillation. So I'm going to find some value capacitor to put in there that's in that range. Maybe a 1500 if I can find one. Perhaps an 1800 picofarad would work, but I need more feedback, and that's how I'm going to get more feedback. So I settled on 1800 as a feedback capacitor, instead of the 2000. I've tried some different tubes in the 6U8 slot, some 6GH8s, 6GH8As, 6U8s, 6U8As, and I got bad news. I'm seeing a lot of variation, especially in the regenerative. Don't be afraid to try different tubes here. So far, this has been the trickiest circuit, this regen. Now I know what they're talking about with AM requiring the regen to be set critically to get good AM. That certainly is showing itself. Once you go into CW and turn the BFO on, it's just like an RF gain control. But in AM, the regeneration becomes important. So I don't really understand what's going on, but I'm going to go to the front end in the next video. I think we have the BFO is drifting because I just changed tubes again. Yeah, this tube's drifting. So again, do experiment with different tubes. You're going to get different effects. So do experiment with different tubes. You may find your circuit just suddenly starts working. I don't even know what tube this is. Let's take a look. What is this thing? Ooh, this is a Japanese 6U8. Made in Japan by Westinghouse, Japan. Wow, that's a beauty. 6U8A, that's a late model tube.